I'm Erin Towler, and as part of the Climate and Weather Extremes tutorial, I'm going to be talking about statistical modeling frameworks for extremes. In the previously recorded lecture, dynamical downscaling was introduced, along with the associated considerations of resolution, domain size, model physics, and input data. Dynamical downscaling for regional climate or extremes has both advantages and limitations. Some of the advantages are that the responses are physically consistent and it produces finer resolution data. However, there are limitations. It's strongly dependent on GCM forcing data, it's computationally intensive, and some variables are not well modeled, either due to insufficient resolution or inadequate process understanding. As such, some of these limitations can be addressed through statistical modeling frameworks, or more conventionally known as statistical downscaling, which is the focus of this talk. For instance, statistical downscaling can correct bias in forcing GCM or RCM data. It's also computationally efficient. And this is important since some impact studies often require climate information at finer spatial scales than what is provided by either global climate models or regional climate models that have been dynamically downscaled. And finally, you can empirically derive variables that are not directly available or not well modeled by GCMs or RCMs. However, something to keep in mind is that extremes were not the original focus of statistical downscaling. As such, it's important to understand statistical downscaling techniques that are traditionally used and how they handle extremes. In a nutshell, statistical downscaling relates large-scale climate variables, which we call predictors, to local or regional variables, which we call predictants. We can represent this mathematically as y, the predictant, is a function, which represents the statistical model of some predictor or predictors x. The nice thing about this formulation is that it's extremely flexible. However, because it's so flexible, it can be very difficult to categorize, especially in a neat way, all the different methods. Another key point is that it often requires some data analysis and/or statistical tools. Even though these can be difficult to categorize, we can look to the literature to produce some classifications. These classifications are based on Moran. The first two, perfect prognosis downscaling and model output statistic or MOS, differentiate based on the nature of the predictor. We'll talk a little bit more about this. Either the predictor is an observation or the predictor is the model output. The third classification are weather generators. We'll talk briefly about weather generators and what they are. Many of these methods incorporate MOS and PP aspects, hence the difficult part of categorizing them. Again, I want to point out that different fields use different terminologies, and so there's a lot of overlap between some of these methods. There's also a lot of new hybrid approaches coming out, but again, we'll provide these broad classifications for our purposes here. We'll start with perfect prognosis or PP downscaling. Again, because it differentiates based on the predictor, here we relate an observed predictor, an observed large-scale predictor, to observed local-scale predictants. Once that relationship is developed, it can be applied to any projection, either the GCM or an RCM, to get to downscaled data. The key step to this is to identify informative large-scale predictors. So again, these have to be things that relate in a physically plausible way, things like atmospheric circulation or humidity. And then the second step is to develop statistical model, the function f that relates the observation to the observation. And we'll talk more about these different methods, and one example are regression methods. The key assumptions here is that the large-scale predictor is well simulated by the climate model, and that the statistical relationship will be constant in the future, that it's temporally stable. As I said, we're going to talk more about some of the statistical models commonly used to develop that relationship between the observed large-scale and the observed local-scale variables And I've listed 5 here. The first 2, linear regression and generalized linear models. And then we have other examples like nonlinear regression, analog methods, and extreme value statistics, which we'll talk about later in the playlist in a different recording. I'm briefly going to talk about these top 2 to give us a flavor of what these statistical models can look like. The simplest way to relate 2 variables is using linear regression. Here, y, or the predictant, is equal to an intercept times a slope times the predictor plus some random error term. Linear regression was developed to estimate an expected value or an average, but it may not be appropriate for extremes. Moving to our second statistical model, generalized linear models, or GLMs, are a more flexible approach for modeling responses with different attributes. So linear regression, which we just talked about in the previous slide, models continuous data. And so that is actually a type of GLM. Next, we'll talk about the logistic and Poisson. So categorical data can be modeled with a binomial distribution, or what's called logistic regression. I show the math here just to show you what is at the base of this, if you want to look back later. This is also detailed in this Helsel and Hirsch publication. So what would this be used for? Well, how about with the probability of a wet versus a dry day? And sometimes the number of wet days can be a type of extreme characteristic. So now we're moving a little bit closer to getting at more extremal properties. Or you could look at the probability of being above or below an impact threshold. So again, as we talked about in the state of the science of extremes, the threshold may be subjective, but again, we're starting to move toward things that could be more extreme if we make that threshold high enough. Here, I show what this would look like in R. That's a statistical package. So GLM, y tilde x, and the family is equal to binomial. This will help us predict the probability of exceedance. For integer or count data, we can model that with a Poisson distribution. Again, just showing some coding language here. GLM, or y, it's a function of x, and the family is now Poisson. Again, just showing a little bit of the mathematical representation. So here, we could find out how many hurricanes will make landfall in a year. Now we're getting even closer to extreme events that we might be caring about. Or how many days will we violate the minimum stream flow threshold, something that might have an impact, like being extreme for the fish who need that stream flow to live. Of course, PP statistical modeling has some limitations. It requires a long and reliable observed historical record. It's very dependent on the choice of predictor. And as we mentioned earlier, it assumes that the relationship stays constant or is temporally stable. A bit of a summary of this, PP approach can be tailored to estimate characteristics of extremes, especially those that are not available or well simulated by GCMs. And it's flexible and portable to different users, regions, and subjective definitions of what is extremes. The extreme value theory, which is a talk later in this playlist, is a PP method for more rare extreme events. So model output statistics was the second category that we pointed out, and this relates modeled large-scale predictors to observed local-scale predictants. This can be performed here, and then it can be, once the relationship is developed, it can be applied to a GCM or an RCM to get downscaled data. The key point here is that MOS can only be used to relate distributional characteristics unless the model is run by reanalysis or is in operational weather forecasting. And the main assumptions is that, again, the large-scale predictor is well simulated by the climate model, and again, that the statistical relationship is constant in the future. For MOS, there are several methods that are commonly used. And I'm going to go through each of these: the change factor delta method, the bias correction direct method, the distribution mapping, quantile mapping method. Again, there are a lot of different methods that can be used, and these are 3 ways we've categorized them. There's other ways you could do it, but again, this is based on this Moran paper. So the change factor is the simplest of methods, basically rescaling the observations. So for temperature, it's the difference between the mean control model and the mean future model. And then you add that to the observations. This has also been called the delta method. So the change factor, again, is the difference between the future and the control from the model, and then it's added to the observations. For precipitation, it's the ratio between the future model and control model, and that's multiplied by the observations. So let's look at an example of a probability density function of, say, precipitation for monthly precipitation. Here's our observations, and you can notice that it has this bimodal pattern. And let's say we run our model control for the historical period, and it looks like this. Clearly, you can see that there is some bias going on. The model looks like it's a bit overestimating the observations. And then let's run the model future. You can see that the model future shows that there's a decrease in precipitation. If we apply the change factor using this example, if the change factor is 0.9, which we calculated between the future and control, we would multiply every precipitation value by 0.9 in the PDF. So now you can see the future CDF has that same bimodal pattern. It's just been multiplied by the change factor. So the limitation of this is that the spatial pattern and temporal sequencing of the present climate remains unchanged. And so all parts of the distribution, mean to extremes, are rescaled by a single change factor. So the second method is called bias correction, and it's another way to recalibrate observations to the model output. So here, it's the difference between the control model and the observations, and then you add that to the future model. For the precipitation bias correction, you take the ratio between the mean observations and the mean control model, and you multiply it by the future model. This is also called the direct method sometimes. So now we're using our same example. So using the exact same control run, model future, and observations, now the bias correction factor, if we look at it that way, is 0.5. So now we multiply every future, that's this distribution here, by 0.5, and we get this bias corrected future. So it looks really different than what we had gotten from the change factor. So the advantage of this is that the variability in space and time is from the climate model, not from the present climate. Although, of course, we can't validate that until the future. So that's a limitation. But the limitation is that all parts of the model distribution are rescaled again by a single bias correction factor. The real point I'm trying to make here is that these two calibration pathways don't yield the same answer. And so you have to look at those advantages and limitations that were listed and see what's best for your science question. To get a slightly more complicated approach, you can do ECDF or empirical CDF matching. This is a simple distribution matching approach. This is the same as the temperature BC and precipitation BC, but instead of having a single BC that you use for the entire distribution, you do it on sorted data at each point. So basically, you sort either the temperature or the precipitation and the precipitation. You calculate your bias correction and apply at each paired point. So the big advantage is that the correction is done at each point rather than, like we said, a single value applied to the entire distribution. But the limitation is that it requires the same number of points for the observations and the control in the future. And so here's just an example. If we look at this at each quantile, so biases are calculated for each quantile, and then the calculated biases are added to the future quantiles. We can also take this further. If we do it with the distribution, you require some sort of transfer function. So actually we start down here. If the model value is a 3, we look at what that corresponds to. That corresponds to Q70 in our modeled CDF. We find Q70 in our observed CDF, and then we find the corresponding value of the observed, which is, say, 5 in this example. But again, since we're talking about extremes here, transfer functions can break down at Q100. You never get a different observational maximum. So here in this bottom right, these are our observations. You can see the maximum was 10. So no matter what our model maximum is, so here it's 9, that corresponds to Q100 in the CDF. Find Q100 in our, sorry, that's over here. In our observed CDF, it's always going to be 10. So again, if we're trying to use this to get at extremes, we're never going to get a different Q100 since we're using the transfer function for this. So maybe not ideal for extremes. Of course, there are more elaborate methodologies. Something developed here is this kernel density distribution mapping, which is a nice non-parametric approach and has been found to outperform other distribution mapping approaches. And I put this information up here if folks want to take a look at this R package or the publication by Seth McGinnis. So to summarize, MOS approaches are very commonly used. They weren't really developed specifically for extremes though. If we do that observation rescaling or CF, we can change the magnitude of distribution, but it doesn't change the frequency. If we do model rescaling, we capture distribution from the models, but we can't know if that's correct until the future. And both assume model bias is constant in time. The final category were weather generators. Basically, the point of weather generators is to create synthetic sequences that preserve the observed statistics. So let's imagine that observed daily weather data is like a shoelace where there's, say, 50 years of data. Well, what we want to do is we want to generate many realizations or ensembles of the time series that can be used for, say, impact models or ensemble analysis. So we have all these different sequences. Again, they're similar, but different realizations. Well, how can we do this? There's kind of two main types of weather generators. One are based on parametric methods like GLM. We had talked about GLM a little earlier, or two are based on resampling. We're just going to talk very briefly to give us a flavor of what this looks like using these parametric models. So weather generators, to come up with those different sequences, we usually have a precipitation generator at their core. So if we use a simple example, we could model the occurrence, so the wet or dry, with a first order Markov chain. So let's say these are days, so it would be wet, wet, dry, 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 and so on, using that Markov chain. And then we've modeled the intensity with the distribution appropriate for precipitation. Usually people use the gamma distribution. Once we create these different sequences, we can use MOS change factor time series. So let's say we've developed all these sequences, we can add temperatures, say 3 degrees, and we can multiply all the precipitations by 0.9. And this is one way that we can get future from all of these different realizations. So again, you can sort of see how the different statistical downscaling approaches can be applied to these weather generators, or these weather generator sequences. And another key point is that the weather generators can be conditioned on covariates, things like large scale circulation patterns. That's kind of like incorporating PP downscaling. So something like the ENSO or seasonal cycle can be used. And if you're interested in this, I put a reference to the Katzenführer paper down here, where they model things based on ENSO. To summarize, using weather generators for extremes, really weather generators were developed to provide additional realizations or ensembles of observed time series. But long synthetic series can be used to get at probabilities of extreme characteristics. So they do have that advantage. The precipitation generators are really at the core, but it can be flexible. We mentioned the gamma, but again, the extreme distribution could also be used, and we're going to talk about that in a later recording. I also, to round things out, I wanted to talk about two commonly applied statistical downscaling techniques because they incorporate these different statistical downscaling techniques we've been talking about. So BCSD, developed by Andy Wood, bias correction with spatial disaggregation has been used in a lot of downscaling, and constructed analog-based techniques. Again, these are all variations on things we talked about earlier, but these are two that have become more common. And basically, the predictant is a finer scale of variable climate Z using some statistical model of a coarser climate variable Z. And I just wanted to point out that there have been large efforts to apply different statistical downscaling approaches. This is developed by the U.S. Bureau of Reclamation, and it provided CMIP3 and CMIP5 climate and hydrology projections for the U.S. using several downscaling methods. So you can see the URL down here if you're interested in these. So you can see BCSD as well as LOCA, which I'm going to talk about in a second. There's also been several intercomparisons of statistical downscaling methods that have been done. Again, they all have different advantages and different disadvantages. Many have problems with wet days, wet dry spells, extreme events, and most methods have problems with spatial scaling and interannual variability. And you can check this article by Ethan Gutman, which is referenced down here. BCSD has been widely applied, but has limitations. It has two steps. First, we apply quantile mapping to precipitation and temperature. That's basically a Moss technique. And then they add a spatial variability component. The main limitation is that this was developed as a monthly technique, so limits changes in shape of daily distributions, doesn't consider daily GCM weather sequences. And it does capture extremes and wet day fractions well, but it's limited to rescaling current weather patterns. The second commonly applied technique is these constructed analog methods. Basically, these identify the n best matching analog days that reproduce a particular pattern. The disadvantage here is it uses averaging, which tends to produce too much drizzle. And so LOCA has been a new technique that's been applied that downscales point by point and avoids the averaging issue that I just discussed. So again, I have some details on the method here, but basically you can take a look at the website yourself. The main advantage is that it preserves those GCM daily sequences. It's better at extremes, avoids drizzle, and scales the final value to be consistent with the model. But the disadvantage is it's more computationally intensive than the other constructed analog approaches. So to summarize the key points, statistical and dynamical downscaling both have advantages and limitations. Statistical downscaling is complementary to dynamical downscaling, and it can address some of its limitations. But extremes were not the original focus of statistical downscaling, and there are many approaches. So really, it's important to understand the strengths and weaknesses of them with respect to extremes. Thanks again for listening. Please feel free to reach out with other questions. I will quickly show you the references. And these will also be available as a PDF. Thank you.